Get bought by a math teacher. Poor phone. All right. So now watch. So how much? So in this new picture, first off, what's this thing squared? What's 2.81 squared? Somebody help me out.
7.896.
7.896. So how much area should be up here? Total. So it's going to include the area that was here and the area that's below negative 2.81. But of course that's the same, right? So how much total area should be above this? All right. Maybe. So right now, I mean, we're just, unfortunately, obviously, we don't have the time to get all the tech. We don't even need to. We don't even supposed to. But I want you to buy into the first row of this chart that I'm about to give you. Yes. Oh, yes. Another chart. Oh, God, Jeff, why? All right. I feel it. Let it flow through you. Yes. It's good. Just take this and just sit there for a minute. Just take it. Just realize this is the last one of these I'm going to give you. Right? So, revel in that realization. Just take stats too, and you can get F distributions and all these. Oh God, forget about it. You need one? The absolute worst thing about this handout, about this chart, is not just the fact that it exists, but notice what it says. Where's the area that this is referring to? To the right. Everything else we've ever done has been to the left, kind of, right? So that's the first thing to realize. Now here's what my attempt to get you to buy into this. So this would be for a single variable. Are you with me? So that's why the degrees of freedom here would be, well, it's a single variable compared to like a population parameter. So it's sort of like two things I'm comparing, so the degrees of freedom would be 1. So that's why this is going to relate. The first row here is exactly the same as a folded over z-score distribution. That's all it is. So to be honest, everything we've done before, we could do using this chart looking at the first row. Believe it or not. We're not going to do that. I'm not going to go back in time and start doing it. No. I just want you to realize. But this is more powerful. So it's like this chart has the z distribution in it. Now, obviously, it doesn't have the whole thing because it doesn't have that many freaking columns, right? But it's got the whole z-score chart in it on the first row. So all these other rows are when I get more and more and more observations and things that I want to use. Degrees of freedom start to go up and up and up. Okay. So, what did we get? What was our squared value of 7.896, right? So where do I see that? Do I see 7.896 almost? The closest I can get is right there, right? Is that cool? And what does it say is in the area to the right of this score? 0.005. Yes, okay, good. That's the whole purpose of what I did up here. I really wanted you to realize. We got this number from the z-score chart. That's the z-score chart folded over on itself. So the z-score squared that I can find here better have the area I would expect it to have. So I could have done it with any of these. I just picked this one and took a square root and got roughly 2.81, and that's how I came back at it the other way. All right, so I desperately want you to at least buy into the first row of this. Okay, maybe. Okay. So often in statistics, we are looking at sums of squares of variables, and we've already seen that a couple times. And actually, I don't know if you guys picked up on this, but in the homework they referenced the sum of squares, the least squares line. I can't remember exactly how they put it, but it's the sum of the squares. And so what they're talking about there is when I do a regression, the way it calculates where the line is it takes the distances from the line to each point, and it minimizes that. But it can't be the distance. You got to square it. The same way when we learn standard deviation, what did we have to do with all the differences? We had to square them, or else it always came out to 0. So when they say the least squares line, it's when you sum up all the square distances, it's making that a minimum. So that kind of thing, summing up the squares of things, happens so often in statistics that this distribution exists because of that. This is all about squared values that I would normally use. So squared sigmas, squared means, squared whatever. Okay, maybe. And that's where this comes in handy. And it's able to handle higher level tests, more and more stuff. Okay. Maybe. So, our first little use of this is a really interesting problem. So on the back of this, I have an example. So I really want this to make sense. I'm going to turn this in a minute, but I want to show you one thing before we get into this. See this little dude here? That's the formula. What does that formula kind of feel like, maybe? Help. All right, so here's what I look at this as. This is akin to a z-score, believe it or not. So chi-square is a distribution, just the same way that z-scores are distributed in a certain pattern, right? So chi-squares are distributed in a certain pattern. I like it. And to be completely honest, this is a very abnormal picture to use, because if I'm in this situation, I could just use the freaking z-score chart then, because that's equivalent. So normally we're talking about higher degrees of freedom. So if my degrees of freedom was 10, the chi-square would probably look like something like this. It's got a really elongated tail. It's not symmetric. So this is the kind of picture you're going to look at, you're going to see if you're looking through the chapter 11 in your book. And if the degrees of freedom increases, this moves over. And when the degrees of freedom gets to be about 100, this is moved so far over that it becomes almost normal. Itself becomes almost normal. All right, let me let all that sink in a little bit. Okay. So, I have a normal distribution that exists, right? It just, so going back in time a little bit, stay with me now. There's a lot to kind of get out before I can talk about all of it. So if I have a standard, normal distribution, this just exists. It just simply exists. And I showed you the formula. We looked at the formula once. It was e to the negative blah blah squared, x minus mu over sigma, all that kind of stuff. It has its own formula that defines the shape of it. Let me just let that re-sink in. Right. But how do we use it? We take like a sample, and we get something, and then we convert it into a z-score, and that falls in this picture. So I have a picture that exists, just like I do for chi-square. I have a picture that exists. For a given sample, I can calculate a z-score, see where it falls, look up areas, all that kind of stuff, right? Maybe even look at p-values and make determinations about claims. All the stuff we've done. So over here, same thing. I can look up, I can have a sample, I can create a chi-square score, I can see where it falls on the picture, look it up in the chart, get areas. So that whole process is going to feel very familiar. I'm just using another chart. Okay. So here the formula was this guy, to create a z-score from a sample that I've taken. And in fact, we had multiples. If I had a percentage, the formula looked a little different, right? But they all relate to the same picture that exists on its own. So the very first formula we're going to learn here is that become an E. And that's just like calculating a z-score. I can see where it falls on this picture. All right, so I just want that process to kind of be felt and understood. So this formula tells me where I am on this picture, which tells me how probable it is that happened, or whatever the situation is. This formula tells me where I fall in that picture, which relates to how probable it is, and so forth. Looking at this chart, I can look up areas. Okay, maybe. So it's very similar process that I use, completely different distribution. All right. So here's what these things in this formula stand for. So the most basic test you can use chi-square for is what's called a goodness of fit. I love the name of that. It's perfect. How well does something fit an expected distribution? So for example, for this, so O means observed. All right, did I put it up there? No, I didn't. E means expected. And that's all we got to know. This is almost too good to believe. There's a lot of math behind this, by the way. This looks, I don't know if you guys agree with me, this looks pretty simplistic. I don't know if you guys agree with that statement. It's almost like, that can't be right. There's not enough shit going on. But there's so much behind this. It's insane. The history of this equation, I'm not going to get into. But it's beautiful the way it all boils down. And you get this, and you're like, that can't be right. That is right. Okay, good. All right. And why does this kind of make sense? If I expect, is this good enough? Yes, this is beautiful. This is perfect. This is your classic problem to do this with is M&Ms, right? Because then the teacher can go, I don't have enough money to buy you all bags of M&Ms. I could actually, maybe I'll do it. And you just have everybody kind of see the distribution, and the number, the n keeps decreasing. That kind of thing happens. So here's the thing. If I expect that my M&Ms will be uniformly distributed, I'll have the same amount of each, and I have a bag that has 42 total M&Ms in it, right? And there's 6 colors. That means each color should have had 7. There should have been 7 of each. Does that make sense? So they got to tell you what you expect this to be. So very often they can be very specific. They can say, well, I expect it to be 10% green and 20% orange. And then you would just do 20% of 42 and 10% of 42, and that's the number you would put here. So they have to give you information about what the expected is. And then the observed, they should just look at their data and plop it in. So here I said I got 5 brown, 7 green. You just plop them in. Now, if it was perfectly uniformly distributed, meaning all the colors got the equal numbers, what should this be? 0. I love it. Which means my chi-square score would be 0, which means, well, we'll get into it, but I would not have found evidence to reject the claim that they're the same. So my null is always kind of like that they're the same, and I'm trying to show that these are so different that no, they can't be the same. So that piece should feel very familiar. The bigger this is, the bigger this chi-square score is, the more evidence that it's not 0, that it's different from that. So realize that. If they were exactly the way I expected it to be, all these would be 0. This would sum up to be 0. So chi-square would be 0. So how different from 0 is that not? So I wouldn't have found evidence that they're not the same. They are the same. So here, I can't, again, for the same reason we couldn't do this before, why can't I just go, well, they're not the same? Screw your test, Jeff. They're just not the same. Why is that not good enough? We know why. We know why. If I go out and look at some gas stations and get a gas price, and I'm like, well, that's not the same thing you thought. I'm not going to do the test. It's not the same. Screw you. Why can't I just stop there and just say, what I got is not the same as this? I'm done. Why can't I do that?
Because it's just a sample.
It's just a poor little sample, right? And we're talking about the population of M&Ms. I like it. Cool. Maybe. All right, so to do this correctly, you really should get many, many, many bags of M&Ms and do a stratified sample from all of them. Because your one bag could be an outlier by itself, right? Okay, I like it. Maybe. So let's pretend like that happened. Okay. So how are you feeling? You feel great. I know you do. You're like, why is this not over? Okay. But the actual math of this is just really simple. You subtract them. Ooh, to see how different your observations were from your expected. You square them so that you kill all the negatives. And then you divide each by what you expected. Bam, 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 bam. So you sum them up and I get 3.143. Now let's talk about how to get this. Chi-squared critical. That's like your rejection region. So when I do this formula, this is like my, I don't want to say chi-square star. It gets to be multiple things. But this is like my chi-square star, like Z star. This is what I calculated for my sample. This is going to be related to the rejection region. So let's talk about how to do this. Where did they get this from? Degrees of freedom. There's 6 categories here, right? So then n minus 1, the number of categories minus 1 is 5. So I got 5 degrees of freedom. I love it. So there's no way in hell, I want you to really understand, I could do a z-score, or a t-score for that matter, test on any single color. This is so much more powerful than that. I'm doing all the freaking colors at once. That's an immediate show of how powerful this is. The first row is z-score. It's all the z-score stuff you've ever done is basically captured in that first row. How many rows are on that thing I just gave you? A lot. So every time you go another row up, it's another category that is able to handle that z-scores could never hope to. I really want to get this across. And of course, you know, got to let it sink in over time. So don't freak out yet. Oh yeah. Okay, so let's talk about how to get this. So degrees of freedom is 5. I say here that alpha is 0.05. So let me draw this little picture. So I've got, wow. So I want to show that it's definitely, now why do you think, this is always going to be a right tail test. And that's one reason why they build the chi-square chart to be the way it is. Because 0 is my null, and I think it's different from 0. And how many directions can I go away from 0 in this picture? 1. So it's always going to be here, because anything down here is not different enough from 0 to say that there's truly a difference. It's way up here that I got to go. And what area is in this tail? What area is in there? Same as always. What's alpha? 0.05. Same as always. Same as before. Right? Stay with me now. We will get to the point where we do 2-tail tests here. But for right now, this is going to be a 1-tail test. So this is going to be 0.05. So if you look up 0.05 to the right, 0.05 to the right of the critical value, and I stop, I go down and I stop, where do I stop? 5, and I get 11.071. That's where I got 11.071 from. All right, let me stop there for a minute. Is everybody able to get that 11.071 themselves on that chart, on the chi-square chart? Yeah. All right, cool. Here in a minute, we'll just do a quick fire finding chi-square critical stuff here in a minute. So that's my rejection region. So right here I could say, I'm just going to get to the point on these, by the way. But if I were following all the steps, right here I could say if chi-square star, whatever you want to call it, was bigger than 11.071, we would reject that they're equal. We would show evidence that they're not equal, that there is a difference, that it doesn't follow that distribution, right? So did we get far enough away? We got 3.143. Did we get far enough away? No, we didn't. So we have not found evidence to say that they're not the same. So right here, we have not found evidence to reject the claim that they are uniformly distributed. It was not different enough from a uniform distribution. It is different. There's a lot more blues, right? There's a lot less reds and browns. Not a lot less, but there's less. But there just wasn't enough difference. The minute chi-square is not 0, there is some difference. But is it big enough difference? In this case, no, because it had to be 11.071 at least. So there's a lot of elements here that feel very familiar. but there's a brand new freaky ass distribution, which I totally understand. Don't ever square root that, by the way. Chi-square, the square is sort of seen as part of the symbol. Chi by itself, that's Dragon Ball. This doesn't really come into here. Some of you guys get that reference, I do. Alright, so let me see if you could see what you can do with number 2. Try to go as far as you can with number 2. And I've given you very specific amounts that I expect. So this should be related to this. But how many people am I talking about? 500 people. So how many people do I expect to have less than 130 cholesterol level? 20% of 500. That's what I'm going to put in the expected. So this is a very specific distribution. Yeah, that would help. Any more back there? There you go. See? All right. What were you guys going to do right now? Just sit and wait. Sure. Yes. Oh, what you got, Chuck? $75. Sorry, 250. 250. Yeah. So there's my expected. Just make sure everybody's on the right track. See where I got those from? Yeah. If this is what I expect to happen, this is what they're normally distributed to be. And I'm trying to see if this group matches the general pattern. So if I took 500 people from anywhere, I would expect them to have this. That's what I expect. Now what would go here, for example? What's here? 120, because I observed 120 that have less than 130 cholesterol. I like it. Keep going. Oh, geez. Hopefully we got that 40 down there for the rest.
Yeah.
Gilligan's Island and the rest. I'm never going to give you too large of a sample, to be honest, but I mean, you could realize you could use list 1, list 2, list 3 here if you wanted to, but it's not that difficult to just do this straight up. Like what goes here?
400.
Yeah, because the difference there is 20 squared is 400. The difference there is
8100.
in 90, so squared is 8100. 75 squared is,
5625.
who is it?
5625.
And then this will be 35 squared.
1225.
Let me stop there for a second. Everybody see how that's arrived at? And the beautiful thing about this is I don't care that it's more or less. The whole test is all about, does it match what I expect them to be distributed? So the negatives and positives, I square them anyway. They all come out to be positive. So it doesn't matter if they're more or less. I just want to see how different is it. And in here, I take each one of these and divide by the E. So this first one's easy. That's 4. Yay, Jeff.
54.
The next one's 54?
Yes. 32.143.
Who?
32.143. 16.33.
16 point?
3.
16? Point. Does everybody see where those numbers are coming from? Did you guys get those numbers? This is the time. What happened? So what's up? So I took, for example, this tells me to take all these, which are all here, divided by these, which are here.
Oh.
So 400 divided by 100, 8100 divided by 150. So if you were doing this in your calculator, you could say this list equals that list divided by that list. Bam. It would populate it if you wanted to. And then what do? What's the formula for chi-square tell me to do?
Add them all up.
Yes, sum these up. So if I add all these up,
106.476.
was it?
106.476.
So that's related to my z star from before. All right, so let's go back. Let's see what my critical score. I didn't say, so what am I going to assume? Alpha is 0.05. I like it. Right. So when I don't say, that's the one that's used most often. I think I just forgot to say, but we'll say it's 0.05. It doesn't matter if you draw this big old tail, but that's the way it looks for chi-square. It's stretched out, it's skewed to the right there. So, and my degrees of freedom is what?
3.
Yeah, there's only 4 categories, so my degrees of freedom is 3. So if you look at 0.05, degrees of freedom is 3, 7.815. So how do we do here? Where are we at? We're at 106. So we're over here on we're here on my backpack, I think, right there. Right? Did we pass this test?
Yes.
Did we find out? Yeah, we passed the hell out of this test. Which, if you look at it, do you see how right here there's a lot less, and then there's a lot more, and then there's more there? I mean, every single time they are quite different from what I expected them to be. Whereas here, they were different, but not really that different. So we failed this one, but this one, we completely succeeded. You guys see that? So what does that mean? Don't even put it in the language of so on this island. Was it an island? No, a secluded area, Jeff. I like it. Secluded area, eating a certain diet. So just like the old Mediterranean craze, and we're all like, why are they doing great? Let's figure it out so I can eat the same shit. Same thing here. We find these people in a secluded area. We're looking at their diet because the cholesterol levels are just way better well, actually here it's worse, isn't it? Is this cholesterol levels?
Yeah.
Ooh, I don't want to. So we want to stay away from the diet.
Okay.
Right? So this is evidence then that their cholesterol level distribution is the same or different from the general. It's different. We found evidence that it's different. This is way far away from zero. In fact, how far away is far away enough for this problem? That's far away enough.
What is 7.815? So chi squared is x is 106.476. What?
So this is chi-square star. So remember, when we did the hypothesis test, there was a z-score we calculated, but there was a z-score that told me how far away enough was.
Okay.
And remember, this is not, for a degree of freedom of 1, all the chi-squares are the squares of the z-scores, like we did earlier, right? We squared 2.81 and we saw what was happening. Once you get to higher degrees of freedom, it's not quite that simple, but it's still kind of roughly doing something. That 7.815 is like not quite a square of, because it's a little more layers on top, but it's related to a smaller z-score. So it's exactly like the rejection region, like normal.
Okay, so
These are always going to be...
So that's chi squared and that's chi squared star.
Exactly. I love it. I love it. Just like z and z star with a normal hypothesis test. It's exactly the same purpose for both.
So the higher the chi-square you get, the stronger the evidence is for what region?
Yeah, depending on what the cutoff was. I mean, if the cutoff was 106.3, then it would have been, oh, we barely got it.
Okay.
Yes, cool. Yes.
So the cutoff was 7.81, and we're way ahead of that, right?
We're way past that.
Okay.
I love it. Okay. I like it. Maybe.